So now we've come to the very last part of the last lesson of this first edition of the course Paradigms of Computer Programming, Louvain X 1.01. We hope you enjoyed the course, despite some birthing pains in the beginning, problems with installing Mozart, little problems with Pythia, our coding automatic system for grading coding exercises. So we very much appreciate all your feedback on the forums. And as you noticed, I was quite active on the forums discussing with many of you and explaining many things. So I think that this course really presented many ideas to many of you. So we hope you enjoyed it, despite the little birthing pains. If you are a student, we hope that it gives you an incentive to continue studying programming and to do programming. Programming is a very exciting area, especially now when we're still in the middle of changing human society through programming, through the internet. But what makes it work is programming languages, programming concepts, abstractions. That's what enables this whole series of transformations in human society. So we hope that if you're a student, it gives you an incentive to go into this area. If you're a professional, you're already in the area, and our statistics show that at least 2/3 of you have at least a bachelor's degree. So you are already seasoned professionals. We hope that we were able to give you some new insights here and there and hold your interest. If you're looking at me, then you've managed to stick around till the very end, which is good. So we are using and developing Oz. So Oz is a research language, and Mozart 2, the new virtual machine, for a number of projects in education, but also research in programming language and in distributed computing. The old Mozart 1 system has served for a number of PhD theses of students, and maybe you're familiar with how graduate students work after 15 years of developing in Mozart 1. The system was no longer in a state that it could be maintained anymore, so we did a completely new virtual machine, 64-bit clean. This was Sébastien Durand and Yves Girardin, who were the main implementers of Mozart 2, with help from a number of other people, and this is still ongoing. So we're always looking for help, and you're welcome to join the community. If the strange syntax of Oz hasn't made you completely freak out, then maybe you're interested in the kinds of research that we're doing. So just go to the Mozart users mailing list, see the website, or send me mail. And a final point, we are of course going to continue to improve this course. So I would like to thank all of you for all of the very useful feedback you've given to this course to improve it, so your successors, people coming after you, will see a better course, and it will be largely because of you that a lot of the course will be improved. So if you want to give more feedback and comments, of course, it's all very, very welcome. I would like to make a final reflection on programming. We've discussed kernel languages and how programming is organized into different ways of thinking, paradigms, and how these are connected to each other, the ways that the kernel languages are related. In fact, all of this is not arbitrary. So I'm convinced that programming languages are not just arbitrary inventions of the human mind. I'm convinced that programming language design is a science of nature, like physics. Yes, like physics, where we try to understand nature, programming languages are the way to understand complex systems, how to build and model complex systems, where the world consists of systems. A system is a set of component parts that interact in some well-defined way. So the whole world can be decomposed into different kinds of systems that operate and interact in interesting ways. So in terms of building systems, programming and computer science in general is the most advanced discipline for building complex systems. So here in this diagram comes from Gerald Weinberg's book from 1977, An Introduction to General Systems Thinking, a very nice book. So we organize systems. So we have two axes. One axis is the amount of randomness in the system, and the other axis is the complexity, the number of components in the system. So systems with little randomness and little complexity, we call them machines, clocks or automobiles. Organized simplicity in Weinberg's term. Now, systems with a lot of randomness, like gas molecules in a box, are what Weinberg calls aggregates. And these molecules are hitting each other in all kinds of random ways. And we can use science to describe both machines and unorganized complexity. So machines, for example, Newton's laws, electronics, so on, mechanics, organized complexity, statistical mechanics, the gas laws, and so on, we can understand. But the part in the middle here, the white part, is the part we do not understand well. And this is what Weinberg calls systems or organized complexity. Systems that are complicated and have some randomness in them, but have very large number of components. How do they work? This is actually a very poorly understood area that we're still very much working on. And computer science lets us explore this area in both ways by advancing these frontiers between the shaded part and the white part. Computer science design, building software, or simulation, all of this advances our understanding of systems, and these two lines here are moving in, and it's programming that is the vanguard of this development of understanding complex systems. And each newly discovered programming concept advances the science of building complex systems. So programming and programming language design, and especially successful languages, they are successful because they model some essential aspects of complex systems. Otherwise, they would not be successful. Programs, operating systems with 20 million lines of code, large operating systems today, they work because we use the principles that allow them to work, so we have understood some of this science. So again, programming language design is a science of nature, like physics. So that's what I want to finish in terms of programming paradigms. And now, for further study, in fact, we've only scratched the surface. As you very well may understand in this one course, programming languages is a field with an enormous number of developments, scientific developments, practical developments, very fast moving. If you want to see the taxonomy in a nice poster, you can go to this site and get a paradigms poster. And in order to help you further, I have compiled a short bibliography, very idiosyncratic. I've just picked and chosen a few things that are interesting, that helped me understand programming, and hopefully will help you understand it. Not all these works are focusing on programming language. Some of them are completely different, but they've all helped me understand programming, and I hope that you will all go out and do things and understand programming better and build systems. And I hope that this course has helped you, and that you can see that programming is a unified discipline. It is not just a patchwork, that it is possible to look at programming as a comprehensive and unified discipline. And I hope that this has changed your way of looking at programming, and for the better.